CPU slicing, the performance cheat code nobody talks about. Hello and welcome to episode number 13 of the Unity Performance Task Force podcast. I'm your host, Ruben from the GameDev.guru, and as usual, I'll kick things off with a question for you. Have you ever optimized everything you possibly could, squeezed every last drop of performance from your systems, and still came up short on your target frame rate? Sounds familiar? If so, this episode is for you. Today we're talking about CPU slicing, one of those forgotten techniques that most developers either don't know about or actively avoid. Why avoid it? Because it feels like cheating, like you're gaming the system somehow. But here's the truth. In game development, we cheat all the time. We fake reflections with cube maps. We fake shadows with blobs. We fake entire worlds with skyboxes. That's not dishonest. That's smart. We live with constraints. We work within budgets. And sometimes the cleverest solution is the one that bends the rules a little. So let me ask you this. Have you ever eaten so much cake that you couldn't handle another bite? Of course you have. And what did you do? Did you throw the rest away? No. You saved it for later, maybe an hour later, maybe just a few minutes later when your stomach settled. That's CPU slicing in a nutshell. When you have too much work to fit in one frame, you split it across multiple frames. You eat your computational cake one slice at a time. Here's why you'd need this technique in the first place. Sometimes in game development, you hit a wall. You've optimized everything. You've profiled, refactored, cached, pooled, batched. You've done it all, and you're still not hitting your target frame rate. Or maybe you just don't have the time to optimize further. I'm not here to judge. This is the real world. Not every project has unlimited resources. Even when you do have time, there's a hard truth about optimization work: diminishing returns. When you start an optimization pass, you grab the low-hanging fruit first. Big wins. Maybe you save 10 milliseconds per day of work. Fantastic. But after a few weeks, those gains shrink. Now you're saving half a millisecond per day. After a few months, maybe 0.1 milliseconds. You're spending full days to shave microseconds. That's not because you're doing bad work, that's because you're being effective. You tackle the big stuff first. What's left is small. And at some point, you hit the ceiling. No amount of traditional optimization will push you past it. That's where CPU slicing comes in. So what is CPU slicing exactly? It's simple. When your workload is too big for one frame, you split it into chunks. Then you execute one chunk per frame, or several chunks spread across multiple frames. You're still doing all the work, you're just not doing it all at once. Let me show you a more technical view. Let's say your target is 60 frames per second. That gives you about 16.6 milliseconds per frame. But right now, you're only hitting 30 FPS because your frame takes 33 milliseconds. Frame 1 starts. You run script 1, script 2, script 3. 33 milliseconds later, frame 2 starts. Way too slow. Here's the trick. In frame 1, you run script 1. In frame 2, you run scripts 2 and 3. In frame 3, back to script 1. In frame 4, scripts 2 and 3 again. You alternate. Suddenly, each frame is faster. You've split the cake. Going back to the cake analogy, if you can't eat the whole thing in one sitting, just eat half today and half a few hours later. Your stomach will be ready. Same with the CPU. You're just talking milliseconds instead of hours. So how do you actually do this in Unity? First, I recommend importing my CPU slicing toolkit. It's included in the Performance Task Force membership, and it's also available for free on my GitHub. It's just a couple of scripts, nothing fancy. You download the zip, drag the folder into your Unity project, done. Next, you define your buckets. A bucket is just a collection of work. Maybe it's a group of AI behaviors. Maybe it's a set of physics calculations. Whatever makes sense for your game. The goal is to balance the buckets. If one script takes 10 milliseconds, put it in its own bucket. If 3 scripts each take 2 milliseconds, maybe they go together in another bucket. You want each bucket to take roughly the same amount of time. Let's say you aim for 5 milliseconds per bucket. Then you execute one bucket per frame. Boom! You've sliced your CPU work. Third step, assign work to the buckets. This is where you tell the toolkit which behaviors belong to which bucket. Fourth step, execute the buckets in alternating frames. The toolkit handles this for you automatically. Let me walk you through a real example in Unity. Imagine you have 3 AI behaviors: attack, chase, and spellcast. They all run every frame. Let's say chase is expensive because of pathfinding. It takes 6 milliseconds. Attack takes 2 milliseconds. Spellcast takes about 1.6 milliseconds. Total cost per frame, almost 10 milliseconds. That's a lot. First, we open the profiler and confirm our hypothesis. Yep, chase, 6 milliseconds. Attack, 2 milliseconds. Spellcast, 1.6 milliseconds. Now we define our buckets. Bucket 0 will contain just the chase behavior, the expensive one. Bucket 1 will contain attack and spellcast, the cheaper ones. Bucket 0, 6 milliseconds. Bucket 1, about 4 milliseconds. Not perfectly balanced, but close enough. Now we assign work to the buckets. Open the Update Manager script from the toolkit. You'll see an interface called iBatchUpdatable. This interface has one method, batch update. Go to your AI behavior scripts. Make them implement iBatchUpdatable. Rename your update method to batchUpdate. Make it public. Then, in the onEnable method of each behavior, register it with the Update Manager. Call updatemanager.instance.registerUpdateSliced. Pass in this and the bucket number. For the chase behavior, we use bucket 0. For attack and spellcast, we use bucket 1. Don't forget, in onDisable, call updatemanager.instance.deregisterUpdate. Pass in this. Otherwise, you'll try to run behaviors on destroyed objects. Not good. Finally, add the Update Manager component to a game object in your scene. Hit play. Open the profiler. Take a few samples. Look at frame 1. You see spellcast and attack. That's bucket 1. Look at frame 2. You see chase. That's bucket 0. We just cut the per frame cost by about half. In this example, frame 1 went from 10 milliseconds to 4 milliseconds. Frame 2 is 6 milliseconds instead of 10. This is the exact approach I've used on Quest projects when I was running out of options. It works, it's simple, and it takes maybe 20 minutes to implement. Now let's talk about when you should actually use this technique. Use CPU slicing when you're desperate, when you've tried everything else and you're still not hitting your frame rate target, when you can't find any other area of your scene to optimize. Here's the thing, CPU slicing mostly applies to scripts. If your bottleneck is on the rendering side, or physics, or audio, CPU slicing won't help much. You need significant cost in script execution, update methods, late update, fixed update, that kind of thing. But there's another reason to use CPU slicing, even if you're already hitting your frame rate. Battery life. If you're doing less work per frame, you consume less energy, less heat, less battery drain. Players love that, especially on mobile or VR headsets. There's also a variation of this technique for object spawning. If you need to instantiate 500 objects, don't do it all in one frame. That'll freeze your game for seconds. Instead, spawn 10 per frame. It takes a bit longer, but the experience stays smooth. No freezing, no hitches. Now let's talk about when you should avoid CPU slicing. First, if your scripts drive visual changes every frame, don't slice them. For example, a script that rotates an object every update. If you run that every other frame, the rotation will look choppy, stuttery, not good. CPU slicing works best for logic that doesn't have immediate per-frame visual feedback. AI decision-making, pathfinding, system management, procedural generation, those kinds of tasks. Second, if you're not CPU bound, this technique won't help much. If your bottleneck is GPU rendering, slicing your script cost won't move the needle. You might save a bit of battery, but that's it. Third, depending on your gameplay, making CPU slicing compatible with your scripts can be tricky. You need to think carefully about which systems can tolerate running at half frequency or quarter frequency. Some can, some can't. Before we wrap up, let's talk about alternatives. You could use multithreading, run expensive work on another thread. But multithreading in game development is tricky. Race conditions, deadlocks, Unity's API restrictions. It's powerful, but complex. You could use Unity's job system or dots. These let you execute work asynchronously, often with better performance than manual multithreading. If you have the time to refactor, they're a great choice. But if you need a quick win, if you need something you can implement in an afternoon, CPU slicing is hard to beat. Here's the thing. Getting CPU slicing to work depends entirely on your gameplay mechanics. The technique itself is that simple. Split work, run it across frames. Done. But making it compatible with your specific game, that's where the art comes in. You need to understand your systems, know which ones can run at lower frequency, know which ones need to execute every frame. This is exactly the kind of checklist we use at the GameDev.guru when teams are stuck at the optimization ceiling. We profile, we identify the bottleneck, we figure out which systems are sliceable, and we implement the pattern. Usually takes a day or two, and the frame rate jumps by 5 to 10 FPS. Let me recap the 3 big takeaways. 1. CPU slicing is splitting heavy workloads across multiple frames instead of doing everything in one frame. It's like eating a huge cake one slice at a time. 2. Use it when you've exhausted traditional optimizations, when your bottleneck is script cost, and when the work doesn't need to update every single frame. It's also useful for reducing battery drain. 3. Avoid it for scripts that drive per frame visual feedback or when you're not CPU bound. And remember, the technique is simple, but making it compatible with your gameplay can require some thought. If you found this podcast episode useful, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity consulting is what you are after, book a free discovery call at https://consulting.thegamedev.guru. Till next time.